Welcome to the Deep Dive. It is Friday, February 20th, 2026.
Great to be here.
And we have a really fascinating one today. We spent a lot of time on this show discussing the energy transition. You know, things like hydrogen hubs, next-gen solar, grid resilience.
Right. The green transition gets all the headlines.
It does. But, I mean, if you look at the capital expenditure reports that came out this week, there is a totally parallel narrative running right alongside it.
Yeah.
And it is just as massive and, frankly, technologically staggering.
Yeah, it's the rush into the ultra-deep.
Exactly. The ultra-deepwater frontiers, the hunt for traditional hydrocarbons is pushing into areas that honestly sound like science fiction.
They really do. And frontier is definitely the operative word here. We aren't talking about shallow shelf drilling anymore.
Right.
Those easy reserves, the ones close to shore, they're gone. Or they are already online and producing. What we are seeing now, specifically with the massive news dropping this week, is a push into water depths and geological complexities that were considered completely economically unviable just a decade ago.
Yes. So let's get right into the news peg driving today's dive. The big headline this week comes out of Athens.
The Greek deal.
Right. The Hellenic Republic just signed these lease agreements that are effectively reshaping the Mediterranean energy map. You have a consortium led by Chevron taking a 70% operator stake, and Hellenic Energy holding the remaining 30%.
And the scale of this is just immense.
It's massive. This isn't just a small exploration license. We are talking about 47,000 square kilometers across 4 major blocks. You've got South Crete 1, South Crete 2, south of Peloponnese, and Block A2.
Just to put that surface area in perspective for you, 47,000 square kilometers is larger than the entire country of Switzerland.
Wow.
Yeah, it's huge. But the surface area isn't even the real challenge here. It's the verticality.
The depth.
Right. These are ultra-deep water plays. We are looking at water depths exceeding 1,500 meters.
Right.
And in some parts of that area, it plunges even deeper.
Over a mile straight down through the water before you even touch the mud.
Exactly. And the geology down there is incredibly complex.
Which we'll get into. But I just want to note, this isn't an isolated event. ExxonMobil also recently expanded their presence nearby in the Ionian Sea, so the Mediterranean is really becoming a major hotspot for this.
It's a huge strategic shift, and we are seeing the exact same thing play out globally. Look at India.
Right, the ONGC announcement.
Yes, state-run ONGC just announced they finished installing mega offshore structures at their KG-982 development. That's in the eastern offshore KG basin.
And for India, that's really a matter of domestic security, right? Trying to reduce their reliance on imported energy.
Exactly. It's about energy independence. But technologically, it mirrors exactly what is happening in Greece. As Chevron's VP, Kevin McLaughlin, put it, companies are being forced into these frontier areas. It requires a completely different class of technology.
So let's talk about why they're going to all this trouble. Before we talk about how they get it out, we need to do a little Geology 101. What are we actually drilling for down there?
Well, it's not dinosaurs.
Right. I think everyone has that old Sinclair dinosaur logo in their head.
Yeah, it's a huge misconception. We are not looking for dinosaur graveyards. We are actually looking for ancient algae, phytoplankton and zooplankton.
Microscopic sea bugs.
Basically, yes. Millions of years ago, these microscopic organisms lived in the ocean, died, and sank to the bottom. But the trick is, less than 1% of that organic matter actually gets preserved.
Because usually it just rots away on the seafloor.
Exactly. For it to become oil, it needs to fall into an anoxic environment. That means oxygen poor. Think of a completely stagnant basin, something like the bottom of the Black Sea today, where things don't decompose.
Okay, so the algae piles up in this dead zone.
Right, it doesn't rot. It gets buried under millions of years of sediment, pushing it deeper and deeper into the earth. And that is what geologists call the kitchen.
The kitchen.
Yeah.
Because it literally cooks.
It does. As it gets pushed deeper, the temperature and pressure rise. This cooks the organic matter into a substance called kerogen. And if that kerogen hits the oil window, which is typically between 100 and 150 degrees Celsius, it cracks into liquid oil.
And what happens if it gets pushed even deeper past that 150-degree mark?
And it gets overcooked, the chemical bonds crack even further, and it turns into natural gas.
Okay, so you have this cooked oil and gas miles underground, but it doesn't just stay in the kitchen, right? It moves.
Right, it migrates. Oil and natural gas are lighter than water, and all the rocks deep underground are saturated with water. So thanks to buoyancy, the oil and gas slowly migrate upwards through the tiny pores in the rock.
Floating up. But if it just kept floating, it would eventually leak out into the ocean. We need something to stop it.
We need a trap. Specifically, you need a cap rock. Think of a trap like a giant underground upside-down bucket.
An upside-down bucket. I like that visual.
Yeah, the oil floats up, hits a layer of impermeable, rock-like thick shale or salt that it can't pass through. It fills up that upside-down bucket until it reaches the spill point.
And then any extra oil just spills out the bottom edge and keeps migrating.
Exactly. And you have different types of these buckets or traps. There are structural traps created by faults folding the rock, and stratigraphic traps where a layer of porous sand just pinches out.
You mentioned salt as a cap rock. And I know salt domes are a huge deal in offshore drilling.
They are massive. Salt is fascinating because over geological time and under immense pressure, it behaves plastically. It's lighter than the rock above it, so it literally floats upward through the solid rock.
Like a lava lamp.
Exactly like a lava lamp. It pushes up through the heavier sediments, creating these giant domes. And as it pushes up, it bends the surrounding rock layers upward, creating perfect traps right along the sides of the salt dome. They're incredibly common in the Gulf of Mexico and the South Atlantic.
Okay, so we've mapped the geology, we found the trap, now we have the engineering problem. How do we actually get this oil out of the ground when there is 1,500 meters of ocean sitting on top of it?
This is where extreme engineering takes over, because traditionally you would just build a metal tower from the seafloor all the way up to the surface.
Right, bottom-supported structures, the classics.
Yeah, you have your steel jackets, which are basically giant metal frames piled into the seabed. And then you have gravity-based structures, or GBS.
Those are the massive concrete ones, right?
Huge concrete beasts. They just sit on the bottom by their own sheer weight. Fun fact about those, especially the ones in North Sea, they are so massive that they actually have built-in oil storage tanks right inside the concrete cells at the base.
That's incredible.
And you also have jackups, which are mobile rigs with legs they lower down to the mud to jack the platform up out of the water. But mostly just for drilling, not long-term production.
But there is a limit to all of these.
Yeah.
You can't just build a tower forever.
Exactly. Bottom-supported structures generally max out around 500 or maybe 600 meters of depth. Beyond that, the bending stress from the ocean currents is just too much.
And for these new frontier projects, we are talking depths of 1,500 meters or more, so building from the bottom up is impossible.
Completely impossible. You have to float. And the workhorse for these ultra-deepwater fixes is the FPSO.
The floating production, storage, and offloading vessel. Basically, it's a ship that stays put.
Right. Visually, if you flew over it, it just looks like a massive oil supertanker. But someone built an entire chemical refinery right on the top deck.
But the engineering constraint that always blows my mind with FPSOs is the mooring, the weather vaning problem.
Oh, yes. The swivel.
Right, so you have this giant ship out in the open ocean. If a massive storm rolls in, the ship has to be able to rotate to weather vane, so its bow faces directly into the wind and the waves. If it gets caught broadside by a rogue wave, it could capsize.
Exactly. It needs to spin 360 degrees freely.
But it is constantly connected to the sea floor by rigid steel pipes, the risers, bringing up high-pressure oil. How do you keep a pipe connected to a ship that is spinning around in circles without twisting the pipe until it breaks?
You use a swivel stack. It is the single most complex mechanical point on the entire project.
How does it actually work?
Well, first you have the turret. The turret is basically a giant vertical hole running straight through the hull of the ship. Inside that hole is a structural cylinder that is anchored to the seabed with massive chains.
So the turret stays completely stationary relative to the ocean floor.
Yes, it doesn't spin. The entire ship rotates around the outside of the turret using some of the largest mechanical bearings ever manufactured.
Okay, but the fluids, you have oil and gas shooting up at thousands of PSI. How do you get that from the stationary pipes in the turret into the processing plant on the rotating ship without it leaking everywhere?
That's the swivel stack itself. It sits on top of the turret. Imagine a vertical stack of metal donuts. The inner ring of the donut is bolted to the stationary pipes. The outer ring is bolted to the spinning ship.
And the oil flows through the empty space inside the donut.
Exactly. It flows into the stationary inner ring, out into that open toroidal chamber, and then out a hole in the spinning outer ring. The gap between the moving metal parts is sealed with incredibly high-tech elastomers. It's a mechanical marvel.
And I imagine if those seals fail, it's a bad day.
Oh, production completely shuts down. Replacing a swivel seal offshore is a massive, incredibly costly operation. The material science in those seals is heavily guarded proprietary tech.
Now, FPSOs are amazing, but they aren't the only floating cities out there. You also have TLPs, tension leg platforms.
Right. TLPs are positively buoyant. They actually want to float much higher in the water, but they are pulled down by massive steel tendons anchored to the floor.
So they don't bob up and down.
Exactly. It eliminates the vertical heave, which is fantastic for reducing stress on the riser pipes.
But the one I really want to talk about is the spar platform.
The spar is a totally different beast.
Visually, it's basically a giant vertical cylinder floating deep in the water, like a massive soda can standing upright.
A very deep draft. But because it's a giant cylinder sitting directly in strong ocean currents, it faces a very unique physics problem called vortex-induced vibration, or VIV.
Right, vortex shedding. Because as the deep ocean current hits that massive cylinder, the water can't flow smoothly around the back.
No, it peels off. It creates these low-pressure eddies or vortices that detach ultimately from one side of the cylinder and then the other.
Pushing and pulling the structure.
Violently. It creates a rhythmic oscillating force. If the frequency of those eddies matches the natural resonant frequency of the platform, the whole thing starts to shake. It can fatigue massive steel moorings in a matter of weeks.
So how do you stop a giant cylinder from vibrating?
You install vortex breakers.
Strakes.
Yes, helical strakes. There are these giant spiral fins welded around the outside of the hull.
Like the threads on a massive screw.
Exactly. Those fins disrupt the water flow just enough so the vortices can't organize into that rhythmic pattern. They break up the shedding. It is a beautiful example of passive engineering. You solve a massive structural threat just by changing the physical shape of the hull.
It's elegant.
Yeah.
But let's go even deeper. The floating vessel is really just the hub. The actual extraction, the really dirty work, is happening down at the mudline.
Right, the drilling.
The drill string itself isn't just a simple pipe making a hole.
No, you have an entire drilling package down there. You have the blowout preventer, the casing, and critically, the mud system.
Drilling mud. And we should be clear, this is not just wet dirt.
No, it's a highly complex synthetic fluid, and it serves a few purposes. It cools the drill bit, it carries rock cuttings up to the surface so the hole doesn't clog, but most importantly, it provides hydrostatic pressure.
The weight of the mud holds the well back.
Exactly. The oil and gas inside the rock are under immense pressure. If you just drill a hole, that pressure shoots straight up the pipe, and you get a blowout. The heavy mud sitting inside the well physically pushes back against the rock to keep it stable.
And once the well is drilled, in these modern setups, like in Greece and India, they are leaving a ton of equipment right on the seafloor. The rise of the subsea factory.
It's totally changed the industry. Instead of lifting everything up to a platform, they are putting pumps, separators, and compressors right on the seabed.
Starting with the Christmas tree.
Right. The subsea Christmas tree is the massive assembly of valves and gauges sitting directly on top of the wellhead. It's the primary barrier controlling the flow out of the reservoir.
And then you have manifolds.
Manifolds are great. They sit on the seafloor and collect the flow from multiple different wellheads, mixing it together and then sending it all up to the FPSO through a single massive pipe. It saves a fortune in riser pipes.
But having all this machinery scattered across the seafloor creates a completely unexpected problem. Fishing.
Yes, it is a massive issue.
Because if a commercial trawler drags a heavy net across the bottom and snags a subsea wellhead, it's a disaster.
It can cause a catastrophic leak. It's a huge concern in places like the North Sea, where you have heavy offshore infrastructure right alongside commercial fishing grounds.
Which led to systems like FishSafe.
Right. FishSafe is a unit installed on the fishing vessels. It holds a GPS database of all the subsea obstructions. If the trawler gets too close, it sounds a loud alarm, warning the skipper to pull their nets up. It's a very simple integration of data, but it prevents massive environmental disasters.
So synthesizing all of this back to the news of the week, we have Chevron and Hellenic in Greece and ONGC in India, and they are deploying this exact technological arsenal. FPSOs with swivel stacks, massive subsea factories, complex drilling mud systems, all to tap resources that were completely unreachable before.
They are operating at the absolute bleeding edge.
Which really highlights the strange energy paradox we are in right now. I want to read a quote from the CEO of Hellenic, Andreas Shameshis. He recently said, "While investing in the energy transition, we recognize that hydrocarbons will continue to play a critical role."
It's an acknowledgement of reality. The transition is an and, not an or. We need the green tech, but global demand means we still need the hydrocarbons for the foreseeable future.
And that demand is driving us to do absolute wild things. Just think about what we've covered today. As a final thought, we are building some of the most complex, massive moving structures in human history.
Floating in 1,500 meters of water.
Right. Just to harvest the remains of ancient algae that cooked at 120 degrees Celsius for millions of years, extracting it through a straw with robots on the seafloor.
It really is a race between depleting those easy reserves and the sheer speed of the green transition.
It absolutely is. Well, before we go, I highly encourage you to go online and look up a picture of a spar platform vortex breaker. Seriously, look at those strakes. Seeing that fluid dynamics physics in action on that scale is incredible.
It's definitely worth a search.
That it is. Thanks for joining us on this deep dive. We'll be tracking the progress of Block A2 closely. Catch you next time.